So this tutorial is going to be about the one-dimensional FDTD code, FDTD method. Which is the finite difference time domain method. So, what is the FDTD method? The FDTD method is the finite difference time domain method. And what it does, in a nutshell, is that it takes Maxwell's equations and it discretizes them. So it puts them in a form where we can create them and simulate them. And how does it do that? It uses something called the Yi algorithm. So what is the Yi algorithm? The Yi algorithm does these 4 steps right here. First of all, it discretizes Maxwell's equations, like I said previously. It also discretizes space and time using a very clever method of staggering them. On something called the Yi grid. And the fact that they are staggered is very important, because otherwise this method would not work. And I will touch more on that when we are drawing the Yi grid. Another thing it does is that it updates equations for future values. So it takes your past values in space and time, and it updates them in the future. And last but not least, it iteratively calculates the electric and magnetic fields. All right, so let's just talk a little more about the Yi algorithm, just to show you exactly how it discretizes Maxwell's equations. So, the Yi algorithm will take, for example, Maxwell's first equation. It takes your complex spatial derivative and your time derivative and puts them in a form that we can observe. So it takes them and puts them in a form that we can simulate in the future. So we have all your derivatives equaling additions and subtraction by using this essential difference estimate. And ideally, you have your delta value going to 0. And just to visualize this a little more, if you have a graph and you have any line, and this is the point you want to find, but you have a future point and a past point, what you do is that you take this future point and you subtract the past point, and then you divide it by the difference to find this point. And that's basically what we're going to be doing when we draw our Yi grid. So just to make some assumptions at the beginning, we are dealing with free space. That just makes it super simple. So let's draw our grid. Let's give our grid some parameters. First, we have in the y direction, we have time. And then in the x direction, we have z, or space in this case. And let's give our grid some parameters. Say n plus half, n plus 1. And then for the space part, we will call them k plus a half, and k plus 1. And let's give us a legend here. Let's say that all the triangles are our electric field, and all the squares are all the triangles are our magnetic fields, and all the squares are our electric fields. And because we are dealing with a one-dimensional FDTD analysis here, our electric and magnetic fields are in a single direction, as you can see. So for example, if we were going to find the electric and magnetic field, the combination of both of them at this point right here, using the method that we just discussed, where we take a future point and a past point, we can sort of almost know where our electric field and magnetic field points are going to go. So let's just start filling them out. So let's start with our electric field. If we have a point right here and a point right here, that works out fine, because in this case you have a future value and a past value, and you can interpolate to find this value right here. And then we place our magnetic field, and we are placing that directly at top and directly at the bottom. So then we have a difference between this point and this point, and a difference between this point and this point to get the combination of both the fields at this point. And let's fill up our grid a little more. If we were looking at the field combination at that point, we would have another electric field there, a magnetic field on top, at the bottom, and this gets pretty repetitive. And yeah, so what is the essence of doing this? Well, by doing this, we can take these points and their corresponding fields and discretize both of Maxwell's equations. So let's start with the first one. And let's just put that in a easier form to understand, where we have the time derivative of our H field multiplied by our mu naught value. So let's start with this term right here, where we have our spatial derivative. So we have our electric field, Ex, and we are looking specifically, if we go back to our grid here, we're looking at this point right here. So if these are electric field values, we have a future value subtracted by a past value. So we have a future value of k plus 1 minus a past value of k. And in this case, we have our n, so our time values are constant. So we have a constant time of n plus a half. And then we take that and divide it by the difference, which in this case will be a change in z. Then for the other side, we have a time derivative. So equally, we will have our hy. And if we go back to our grid, we have our hy at n plus 1 and an n. So hy at n plus 1 subtracted by hy at n. And they're both at a constant time and a constant point in space of k plus a half. We take that, divide it by time, change in time. And we do the same for our second equation. We have our H field on one side, and that is changing, in this case, from k plus 1 to k minus 1 if we're looking at this point right here. So k plus a half, minus k minus a half. And there, both fields are at the same time of n. And then that is subtracted by a change in z. And then the same kind of idea for the other side, except we have our electric field. And in this case, our electric field is changing over time, going from n plus a half to n minus a half, and then at a constant point of k in space, divided by change in time. So these equations are basically the only thing left to do now is to get them to an update equation format. And what that looks like is just right here, where you have your update equations, and you just do this by rearranging your previous equations, where you have your future values in time on the left side and the rest of your expression on the right side. So in these equations, there is a term that is currently unknown. So how do we determine the change in time and the change in space? And how we do that is something called Courat's condition. And all that says is that the change in time must be less than the change in space over the speed of light, c. And this represents how much time it would take to propagate one time step. So from that step, we could say that the change in time is equal to the change in space over 2c. And this is what we're going to use when we simulate these update equations. So this is just an example of the simplest form of an FDTD simulator on MATLAB. So first you have your fundamental constants right here. So your mu's, your epsilons, your speed of light is in there. And then you have your units in nanometers to keep it easy, because we are dealing with things of waves, which are very small scale. And then you have some grid parameters. So your delta Z, your delta T, using the Courant's condition right here. Some more grid parameters. Then you have your source parameters. And these will just describe the nature of your source. And then you initialize your electric field and magnetic fields right here to 0 before you start off with your for loop. And in here, you'll be spanning the space of your grid from 1 to NT. And you'll be calculating your equations using the updated equations that we solved for previously. So your electric field, this term is just your source. In this case, we'll be using a regular sine wave as our source. And then our magnetic field update equation right here. And then these will just help with the plotting. And this number right here will just tell you how fast your simulation is going to go. Okay, so let's run this. So as you can see, your electric field right here and your magnetic field, you have your source starting at this point right here. And it looks a little strange right now, and that's because you have the source going in both directions. So you have a source going in your left and your right. And at these boundary conditions right here, the waves are being reflected. And there are ways that you can make it so you have only one source going in one direction, and you can change your boundary conditions such that you can have absorbing boundary conditions or even possibly periodic boundary conditions. But to do those, you would need to change your code. Not significantly, but just to clean up your output a little more. And there's also a possibility of adding a possible like a dielectric slab, so you can see just how the waves will interact with certain materials. And yeah, that is the end of our tutorial. Thank you for listening.